Okay. Let's start some real content. So previously we just reviewed the linear algebra. Yeah. I will spend like there are some like rest of detail that I need some important topic that I need to talk about this linear algebra. So I will spend like the first lecture talking about some other stuff. So all these are in your linear algebra textbook. But because most of the physics or engineering department only takes linear algebra for one semester, so this topic is seldom covered. So I will, but yeah, but I think there are importance and also used for other than this foundation information. So I think it would be good for me to tell you something about this. So this is tensor product and also so-called simultaneous diagonalization and singular value decomposition. This SVD and also Poisson decomposition. So these are interesting topic. Maybe let me just so let me just go about this linear algebra. So this tensor, so this is defined so-called tensor product. So if I give you so-called Hilbert space, or basically two finite dimensional vector space, let's say one is dimension n and the other is dimension n, then you can define another vector space called tensor product. 那么我稍微讲一下，就是我跟一个向量空间dimension 是 n 的话，跟一个向量空间dimension 是 n 的话呢，你可以定义一个新的向量空间，它的大小是它们两个乘在一起，不是加在一起，是乘在一起，就是 tensor product。Okay. The element of B tensor W are linear combination of these. So simply speaking is that all the elements inside B tensor W can be written as some tensor B, some vector B and some tensor W. Let me mark down. You write as this, and it's linear combination of it. Okay. So this is definition. One definition. So if you believe if you know this definition, then this definition will give you the following result. Say that let's say you got some basis for B and some set of basis for W. Then all the elements inside B tensor W can be written as basis, the linear combination of I tensor J. And you just basically. 那我在讲什么？就是说你现在用这个 tensor product 有定义方式，但是one of there are various definitions of tensor product. So there are like more abstract way, but simple way the simplest way to define it is you just define a B tensor W to be a set of vectors, which can be written as linear combination of this, such as I is the basis of B and J is the basis of W. Maybe let me just write. So one easy definition for the B tensor W is you just divide the set. Let's say you take, let's say set I, this set is the orthonormal basis of V, and J is the orthonormal basis of W. And the B tensor W just define the B, let's say this number IJ, I, and then let's say our IJ are all complex. Okay. So we can write down some example. Let's say you take two-dimensional, right? So let's say you can take V. You can take V to be the two-dimensional vector space. So for example, you can write as AB, right? Or you can write as A10 plus B01. So so this is a set, right? AB are complex number, or you can write B as a linear combination of the bases, right? So let's say I write as A0 plus B1. So 0 just 1 just 0, 1. Okay. So now I can write B tensor V. Right? So I can write B tensor V as a set. I can write as a so just for convenience, let's say I can write A0 tensor 0 plus B0 tensor 1. By definition, I just take all the all the Cartesian products of the 0 plus the 1. Okay, the definition. So all the addition and the multiplication are well defined because you take two elements in this set. The addition is just their addition. So you just view 0, 0, 0, 1, 1, 0, 1, 1 as a new basis. So the dimension of is V tensor V will just be 4, right? And all the basis just this. And sometimes like people doing quantum information or like computer science, they are lazy. So sometimes people are lazy. People just write 0, 0 and 0, 1. So people will forget about this whole times nothing. Okay, so
would you write down the matrix of like 1 cross?
You mean this is a vector? Yeah. So I can write it. So yeah. So remember 0 just 1, 0. Yeah. So actually I can write it as this. But notice this dimension is 4, right? So this 0, 0 should be a dimension, should be a vector with 4. Yeah. So actually it's this. Yeah. I will tell you how to write it.
Okay.
Yeah, 0, 1. Yeah. There's a I will tell you how to transform this into this. Yeah. 所以有没有这个听起来会有点抽象，好像反正定义就是这个定义就是你把 orthogonal basis， 然后乘在一起，然后把所有 basis 做出来。Okay. So okay, so this is just definition. So I need to tell you that in terms of vector space, right? I need to tell you that how to add this. I need to tell you that what's the definition of vector addition and multiplication. Oh, so definition is very good. So we'll type we'll type the scalar the w, then this z is the same as if you multiply the first one, it's the same as you both the second one. It's also the same as you. Yeah, basically this is the definition. When z times these vectors defined to be this is definition. And when you take two vectors through the tensor product of V1 plus V2 tensor product with W, then it become like V1 tensor W plus V2 tensor W. Okay, so this looks more abstract, but if you think this example will be just trivial. Okay. And if you add two vector at W, that W1 plus W2, and V tensor with it, and you get V tensor with W plus V tensor W1 plus V tensor W. Yeah, basically this is if you start from this definition, then this will be simple, right? Because you can see that if you times any vector scalar here, it's the same as you times here. Yeah, exactly the same. Oh. And the third one is that so this is the larger vector space. So you can define so you can study the linear transformation on this vector space. And also in particular, let's say you take two linear operators or two matrices from E to B and B from W to W. You can define A tensor B acting on the W. And it's trivial that you just define because A is only by definition A is only defined on B to B. So the natural definition is that A act on B, so become another vector in B, and then B act on W, become another vector in W space, then just do the tensor product. 对，所以这个定义其实是完全就是 tautological， 就是没有任何特别的地方在里面。So the second one is for linear combination. They say you take AI, BI, WI, sum over I, then your A tensor B, apply because it's linear, right? So the property should just A just apply on the single B, and then B apply on single W, and then sum over I. But these are like trivially, yeah. You can just once you know the definition, then this will be immediate. Oh, and then you can also define inner product on the tensor product space. right? So remember that we have defined what's inner product mean in the vector space. So if I give you two vector space, both have their own inner products. So let's say you take psi to be a vector like this, VI, WI, WI, and you take phi to be also in the tensor W, let's say VJ, J, J, and the tensor product would just by definition, because B can be paired with V, right? Because they are sitting in the vector space B, and then W are sitting in the vector space R. So the tensor product should be defined as V inner product with V itself, and W inner product with itself. And you just take all the. So maybe let me do an example for you. Okay, so that we say here. So for example, this is almost trivial, right? So say I take a psi to be, let's say I take psi to be a vector space, it has to be a vector in it, right? So let's say, for example, I take it here, I can do this. Let's say 0, 0 plus 0, 1. Okay, so I just be lazy. I just write 0 as a 0. 0. I write 0, 0 as a 0 tensor 0, and then 0, 1 as 0 tensor 1 to be short notation for 0, 1. And let's say I take 5 to be let's say maybe 0, 0. So it's almost trivial example. If I take these two vectors, then the inner product will be just simple, right? You just write inner product. So notice that 0, 0 and 0, 1 are orthogonal by definition. Why? Because with 0 inner product with 1, 1, right? By using that definition, this should be the first 0 inner product with 1, right? Times 0, 1. Let's say 0. Right? If you use a definition. That definition, right? So that definition tells you that when you do a two vector in the V tensor W, your inner product should be just as a linear expansion of single V tensor with W, because you need to pair with V, right? V need to pair with another V. So for this definition, so the 0, 0 tensor inner product of 0, 1 should be defined as 0, 0, 0, 1. Because these 0 need to pair with this 0, and this 0 need to pair with this one by using that definition. But 0 tensor with 0 is 1. 0 inner product with 0 is 1, right? Definition. Because these are unit vectors. And the 0, 1 is 0, right? Okay. So that means that all these four vectors are orthogonal. 0, 0, 0, 1, 1, 0, 1. Right. So now if I take this side to be 1 over square root of 2, 0, 0, 0 plus 0, 1. And then another 5 will be 0, 0. Then the inner product with this and this will be just 1 over square root of 2. The it is so obvious because you just expand it, right? So you write 0, 0, 0, 0 plus 1 over square root of 2. Let's say 0, 0, 0, 1. Okay, and these are 0. So and this is just 1. Why this is 1 by definition? Because you write as it is. Using this, right? This is 0, 0 squared. This 1. So these are just if you forget about, I mean this should be very good, but if you forget about how to do this, you just go back to it. 这个我稍微讲一下，这个其实没有什么问题，就是说，那你把它写成是，你这个记号上是这样，就是你如果忘记怎么算这些 tensor product 的内积，就回到这个定义。If you 你就回到这个定义去操作，那你就可以知道说，你就放这个定义，那你知道这些0跟1之间的这个 inner product 是多少，你就可以反推他们 tensor product 在 multimodus 在他们的inner product 在 tensor 里面要怎么表示。Okay, so yeah. if you forget about how to do the computation, you just go back to this definition. Because the reason is that you already know what's inner product between VI and VJ, VI and VJ, WR. Right, so any two vector in V and the W can be computed using this formula. 如果你忘了，就是回到一下定义，看要怎么把这东西写出来。那一开始会觉得很不习惯，但是算久就习惯。Okay, so this is the result that the textbook doesn't give you a proof, but it's easy to remember. So let's say A is M times the matrices and B is P times Q matrices. Then one can write the tensor product as a large matrix with dimensional MP times NQ. And this matrix, the form of this matrix is this. Okay, so this means that you just take B and you just take B, right? You just take B is a P times Q matrices and put it as each element of A. 听起来会有点抽象。我这样，就是说，我这样讲，就是说，maybe 我这样讲，我把它写在这里。So this is the actually you can prove it, but the proof is somehow that it's just complicated, but the logic is simple. So let's say I give you a matrices from let's say M times N, right? So this means that A, so I should view A as a matrix which acts on n-dimensional vector and map to n dimension. So A should be viewed as a n-dimensional vector. N dimension, right? Because I take you n-dimensional vector, your A acts on will be n-dimensional, right? So M times N matrices times a dimensional, times a vector with dimensional n, will give you a vector with dimensional n. Let's say A is M times N matrices. And also for B, right? Let's say B is a P times Q, P times Q. So that means that I can view B is a matrix, is a linear operator or a linear transform from Q dimensional to P dimension. Right. So follow the definition. Right? So remember, A tensor B should be defined as similarly, right? You just tensor these two. Right? So we have C with N Q, C on N. So that means that I should view A tensor B as a linear transformation from dimensional n times Q to dimensional m times P. So that means that if I write A tensor B as a matrices, so this is a linear transformation. Right? If I write it as a matrices, then it should be dimension, it should be MP times NQ. Okay, so these are like everything has its own logic. 对，这个只是一个看法，就是跟你讲说为什么 A tensor B 应该是 MP 乘上 NQ 这个大小，因为我们可以把 A 当成是一个线性变换从 n dimension 到双 n dimension， 因为 A 是一个 n 乘 n 矩阵，那 B 也是一样，所以 A tensor B 自动应该是一个从 NQ 维度的向量空间送到 NP 维度的向量空间。那 by definition A tensor B 就应该是 as a linear transformation should be as a matrices should be MP times NQ dimension. Okay, so now the results. So this formula just tell you that this A tensor B as a matrices can be written as this if you know the element of A and element of B. Let's okay. So let me just do some example. Okay, so for example, so you get a vector as a 1, 2, and a 2, 3. So the formula just forget about this. So the formula just forget about it. You just put this 2, 3 into the first one. So just 1 times 2, 1 times 3. So you have 2 and 3, and you just put 2, 3 into 2. You get 2 times 2 is 4, 2 times 3 is 6. 大家看懂这个计算吗？这计算就很无聊，就是你把这个 matrix B 当做一个 you view matrix B as a coefficient and put it into this. Okay. So if you use this notation, then now you can write down all the 0, 0 you can write down the 0 tensor 0 as a 4-dimensional vector. Okay, so the reason is that 0从现在开始，在多数情况之下 ，zero 就是被定义成是一零，有 zero is 1 0 and 1 is 0 1。Okay, so follow that formula. Then I can compute 0 tensor 0. Right? So I choose 1 0 tensor 1 0。按照这个公式，就把这一 So you just absorb 1 0 to be into this. And 0 into this. So you get 1 0 0 0. That formula, right? And then you can write it 0 1 is 1 0. Yeah. Right. So this is just let me just say again, you just do this guy and put into this. So you get 0 1 0. Okay, so 1 0. You get 0 1 tensor 1 0. So we just get 0 0 and 1 0. Okay. Okay. And finally, 1 1 will give you 0 0 0. So this notation just actually it looks like stupid that I just represent this 1 0 0 and this 1 as 0 0 and 0 1 as 0 1 and the 0 0 1 0 just 1 0 and this is 1 1. 还没有，这就只是一个 notation. Okay. Oh, but one very slightly non-trivial is that if you write 0 0 0 1 1 0 1 1 as a binary representation, then 0 0 becomes 0, right? So this is binary representation. So you get 0 0 0 1 1 0 1 1。就你选二进位置的话，00就是0，01就是1嘛，10就是2，11就是3。大家知道everyone knows familiar with binary. So you can see that if you represent this 0 0 0 0 1 1 0 1 1 as binary 0 1 2 3, then actually this is the same as 0 1 2 3. So nothing is. I mean, these are not that's there is no magic here. Okay. And so yeah, so another example is that you can also do it. Let's say you can also compute the tensor product between poly x and y. Example. Okay, so remember x is 0 1 1 0. So if you compute the tensor product with x tensor y, you just put 0 1 1 0 and y with poly. And you know y is 0 minus I 0, so you just probably. Okay. So notice that so in a physical sense, that you can imagine that x is the operator acting on the first qubit, and y is another operator acting on the second qubit. So x and the x tensor y is the operator acting on two different qubits. X and on first qubit, y tensor on the second qubit. So yeah, 就是定义这个微型。Okay, so these are like simple example. For example, okay. So if I give you a fixed state psi, then some people so we will usually use psi tensor k. So it means that this psi will be tensor itself k times. Okay, so for example, psi 2 means meaning that psi tensor psi. So for example, if you take a vector psi to be 0 plus 1 divided by square root 2. Okay, so this is just a vector. If you write down as a 2-dimensional, just 1 square root 1 1. Peace. Okay. So these are linear algebra notation, but you can use a bracket notation, right? Write as 0 plus 1 divided by 3. And you can write out psi tensor. Psi is reason. Right. So you write as this tensor is. And by definition, you can expand it, right? So just 0 tensor 0, 0 tensor 1, 1 tensor 0, and 1 tensor 1 with coefficient half. And then write as a product form, just this tensor is, then you just have it. So if you use this notation, these are basically bracket notation, and you can also expand it as a linear. You can expand all the components. And this is the same as 0, 0. This is 1, 0, 0, 1, 0, 1. Yeah, so everything is consistent. OK，这个就是记号了，这两个记号都可以，对，只是比较常见的是这个记号。So this notation is more compared to that one. Okay, so at least from here, you will notice the thing that if I want to create a uniform superposition, I want to create a uniform superposition of this, then I can do the tensor. I can just take two states. Each state is the same as 0 plus 1 with divided by square root. If I tensor this state twice, then I get all the superposition with equal weights. And so this is so if you do like k equal to 3, then you get similar results. So remember, let's say psi is 0 plus 1 divided by square root. If you tensor it 3 times, right, and do it 25, then you get all the bit string with dense string. 我在讲什么？就是说你现在如果拿0跟1除上 square root of 2的话，如果你 tensor 3 times， 那你会得到 all the possible bit string with dense string. There are 8 of them, right? This is hopefully this is obvious. You got all 0, 0, 0, 1, you got 3 of them. You get total 8 of them. And then there are all equal weights. 1 over 2 square root. And the written as a vector is basically net space. So this example just tell you that if I want to create all the superposition.
So the L2 norm stays preserved.
Yes. So you get 1 over 2. Okay, so previous the definition of tensor products. Okay, so now we move to another small topic. So this is called operator function. I think it's everyone knows about. So it's like I give you a matrix. I give you a matrix. You can basically if you have a function defined complex, then you can define this. You can most of the cases you can define this function acting on the matrix. So this is why in your linear algebra, right? Maybe you heard about professor tell you that you can compute so-called exponential of a matrices. 对，大家有听过？前期代数的时候，有没有老师有没有教过可以算一个矩阵的 exponential？ Okay, so basic definition is so this definition is simple when A is a Hermitian matrix. The reason is that when A is a Hermitian matrix, then the previous lecture tell you that there is a so-called spectral decomposition, or basically you can diagonalize this A into this into its eigenvalue finds this eigenvector, right? So basically I can write A as this form, so I can define f of A to be f apply on this A, and then take the same, and so this is defined as a matrix called FA. Let me quickly recall what you guys learned in linear. Actually, this definition is very natural. The reason is that if you write f in terms of polynomial, then f of A will be just it's exactly the same as these definitions. Okay, so for example, let's say I give you a matrix Hermitian, right? So in your linear algebra course, then since A is a Hermitian, right? So you can do a diagonalization on A. So your professor will tell you that you can write A in terms of let's say U du inverse. Such D is diagonal. 有些人家都有学过嘛，有些人家跟你讲说这个矩阵如果是 Hermitian， 那你可以把 A 写成是 unitary times unitary， 然后中间有一个对角号，对，D 方个。 And obviously that if you write A as this way, then obviously the A to the K will be just U D K U inverse. 这个是虚谬，就是这个证明就so proof of this is mathematical induction. So for example, let's say A square, we just U D inverse U D U inverse. Right? But this U inverse U is identity. So you can use D square U inverse. Okay, so similarly, that it's easy to check that U A to the K will be used D K. And but D is diagonal, right? So D is just all the eigenvectors, all eigenvectors lambda 1, lambda 2, etc. Right, so if you do a power of K, you get it power. So that means that this A to K is exactly the same as A. The difference is that their eigenvalues are different, but eigenvector is the same. So that means that eigenvalue is different, but eigenvector is the same. So eigenvalue is different, and eigenvector is the same. 定义就是说，你写下这个定义的时候，你要把 A 写成 eigenvalue 跟 eigenvector 的这个形式之后，你会发现 for any polynomial, right? The eigenvector is the same. The only difference is that these eigenvalues are different. So that means that if you count, then you can, let's say you can try to expand this f, right? Let's say you can expand it as a k to the xk. So the natural definition for f of a would be defined as just define as a to the k, and then so aka this aka apply on this eigenvalue, would be just change this to f of lambda 1, f of lambda 2, and f of 这个应该没有问题吧？就线性代数。我们刚才在讲高中。So for this example that, for example, let's say you can compute this exponent of theta t. So this is the Polyc vector, which is 1, 0, 0, minus. So exponential theta t we just exponential f, because for Polyc z, let's say so for Polyc z, this is diagonal. So will be trivial and say this is 1, 0, 1, or 0, right? So exponential theta z, we just exponential theta z on it. Okay. By definition, because these are diagonal, right? So when you write it, it's just this function apply out. Just change this z to be the eigenvalue. And these are like quantum mechanics exercise. But so if you take any v to be any real three-dimensional vector with three-dimensional vector with theta as a real number, then you can compute so-called exponential I theta v dot sigma. So sigma is a three-dimensional, is a polynomial display. So v dot sigma will be in the notation, but it's back notation, but it's basically another 2x2 matrices. And you can compute this exponential and you will get this. So you can start from the definition of exponential just using the definition, using a higher extension of exponential, then you can prove. So I can prove this. And this is somehow like usual exercise in quantum mechanics. But yeah, let me just quickly prove it. Because we may use this in the future. 大家看懂这式子吗
You have to first create explanation for a
so basically you need to notice that so this is the band notation. So B is a three-dimensional vector, and sigma view as a three-dimensional vector, but each component is a matrices x and y. And the definition of B dot sigma is defined as this. So this is a two-dimensional matrix, 2x2 matrices. Sum d1 times poly x plus d2 times poly y plus d3 times poly z. So these guys are 2x2 matrices and without explanation. So these are 2x2 matrices. And this formula tells you that if you want to compute exponential of these 2x2 matrices is the same as you just take a cosine identity plus I times sine as this original matrix. 这个也算是 simple exercise。好，我要证明一下。So I mean I can write everything explicitly, but okay, let me do it. So so remember that x is 0, 1, 1, 0, right? And y is just by the way, so these are I use these to be c minus y. And z is just 1, 0, 1, 0, 0 minus 1. Okay, so usually let's say you type a vector b to be let's say b1, b2, b3. So you can compute the sigma dot d. So by definition, it's just v1 times these matrices. So it's v1 times 0, v2. These are definition of polynomials. v3, 1, 0. Okay, and this is just the easy exercise. v3, v1 minus v2, v1 plus I v2 minus I. Okay, and so notice, oh, there is a fact, but I mean we can try to compute. So let's say I compute the sigma v squared. I can compute square, right? Let's say I compute, I just want to check. Let's say I compute square, so I can v3 divided by v2, 2 minus. Okay, let's say I compute this, right? So you can see that, so the first element is v3 times v3, so it's v3 squared plus v1 I minus v2 times v1 I plus v2. So it's v3 squared plus v1 squared plus v2 squared. Okay, right? Because v1 minus I v2 times v1 plus I v2 is v1 squared plus v2 squared. Okay, and the v are real. So you can see for this component, so we get v3 times v1 I minus v2, but v1 I minus v2 times minus v3. So these are 0. Okay. And these matrices are, yeah, you can check this. This is v1 I plus v2 times v3 minus v3 v1 I plus v2. So these are also 0. And then for the final this one is v1 I plus v3 times this. So it's v1 squared plus v2 squared and plus minus v3. So it's v1 plus v2 squared plus v3 squared. So it's and by definition, v is a unit vector, right? I would say v is a unit vector. So that means that v1 squared plus v2 squared plus v3 squared is 1. Okay, so this is identity. Okay. So that means that this sigma dot v as a matrix is a property that is square is a identity matrices. Okay, so the rest is trivial. Let's say I just for the convenience, let's say I write this matrix as S. So okay, so this exercise just tell you that suppose you want to compute this, it's going to my I theta S. So S is a sigma dot v. Right? So by definition, you can write the Taylor expansion. Right? So you can write as a I dot S plus paradigms of convolution. So it's going to X because summation of XK. Not real paradigm equal to infinity. Well, these are the calculus expression. So the important property is that this S squares itself, right? So that means that the first term is 1 plus IS. So second term. So you can see a second term, right? So second term is actually there's the S squared is 1. So second term will just minus theta squared divided by 2. Because the S is a matrix, this square is identity. That I already proved, right? And for third term, that because S squared is identity, so the remaining is the first. So you just get the single S. Right? You always get a single S, and you get I theta divided by 2. Right, so you can see that you can basically take all the even parts. So all the even part will just be an identity, proportional to identity, because S squared is identity, and S to the fourth is also identity. So you can see this is 1 minus theta squared divided by 2, and then for that one will be plus, right? So you get 1 minus theta squared divided by half. Fourth minus 6. Right, so this guy is the cosine. And so this is for all the even term. And for the odd term is the same. You just take once you take S, so once you take this I and S out. Okay, oh sorry. You take this S out, then the remaining will give you this I times sine. It's exactly the same proof for this cosine, right? Because you just take this one. You just take IS, so the cube is so it's all proportional to S. So finish it. quantum mechanics exercise 有一个神奇的 exercise， 有告诉你说这个 exponential of this Pauling matrix, sum of Pauling matrices can be computed easy. And so you imagine, so actually this is infinite series, right? But once you know this property, then you then compute this. You just compute the right hand side. Okay, and okay, so talk about the most famous one. So famous one, so these are complicated, but amazingly the most important one is this trace. So the given matrix A, the trace will be a sum over the diagonal. Okay. Good. Okay, so the first one is the so-called Sigley property that is trace AB equals to trace B. These are so simple that I can very 1 minute. So this is called Sigley property. This is important because we will use in the rest. By the way, this only holds for finite dimension. Now I will tell you. So you just write definition, right? So A times B for the ij component of A times B, we just summation of AIK BKJ. So if you want to compute the trace of AB, it will be just sum over US compute AB and II.
What does that mean?
What?
What does that mean?
Oh, just sum over K.
Oh,
The internal, yeah. Just. Oh, so this is trace AB, just A times B, and then with II component, right? So if you use this definition, then it will give you like AIK BKI. Not J, right? Because II you get replace this J with I. So you get IKKI somewhere K, guys. And obviously this is dummy variable, IK. So you can replace the order of IK. Then you prove this is trace B. You just replace it, just and change it. It's the same as IK, but I can change this to IK. Yeah. Then become trace B. Everything is, yeah, you can check. It is. Yeah, so we will take a break and do 30. So linearity is trace A plus B equals trace A plus trace B. These are true, and DA, and we're trying to constantly use it. Okay, so this one is called this one is called invariance under unitary or singularity transformation. So it means that if you take a unitary as a trace U inverse, because U is a unitary, right? So complex conjugate is the same as inverse. So notice that the unitary matrix's definition is U. So it means that in unitary that complex conjugate is the same as inverse. So the trace of U dagger is the same as. So now you need to use the signaling property, the first property. Tell me that you can remove this U to the right hand side. So this is a U dagger. Okay, I just exchange the order of U and this. Exchange the order of U and a U dagger. Look at this. But U dagger, U times U dagger. So U dagger times U is the same as U times U dagger is identity. So this is identity. So it's trace A.再讲一下，就是说，这个就是说，你给一个矩阵两边夹一个 unitary 的话，它的 trace 不干。对，听起来没什么用，但是重要的一个事实。So example that so this example is not. So this example tells you that you take a unit vector and make it A. So notice that side tensor side, so this is not a number. This is a matrix. Because this is a cadet. So this is a matrix. When you try to now make these are matrices. Its trace is a number. It's the same as you take the inner product, the A times psi and the inner product with the other. So this is, yeah, you can use this. You can use the trace property to prove this. So this one is not good. You need to check. But remember that trace A times let's say let me check where is. Okay, so this is X. Anyways, it's not difficult. Oh, okay. Although small time. So this is called commutative and non-commutative. I think it is also in your quantum physics, right? So notation. So this bracket means that the commutative of A and B is defined to be KB minus B. So when they are all zero, we say A and B commutative. And this is called so-called anti-commutative. Okay. So these are all common in your quantum mechanics or quantum physics. And in the quantum physics, the professor will tell you a weird results. Say that two permission operator A and B can be simultaneously diagonalized if only if they are complete. I think everyone noticed about or heard this theorem. 这个有没有听过？就是老师有跟你讲说为什么要算这个 computation， 因为老师说如果他们扛的话，他们可以同时被对角化。我听过这个教科书有讲过这个事情。好，反正 so this theorem tells you that if I give you two matrices, if they're commute, they are both permission. There exists a simultaneous common orthogonal basis I. A can be written as this or B can be written as this. So this theorem tells you that A and B can be both written as a diagonal matrices in terms of the same basis I. 不对，就是这个 A 矩阵呢，它是很明显，所以它应该选这样，这不稀奇。稀奇的是，如果 B 跟 A 考虑的话，那 B 可以偷拿 A 的 eigenvector 来当自己的 eigenvector，然后 the only difference is eigenvector. So I give you a matrix A, right? Any permission matrix by spectral theorem can represent as this one. But if A and B commute, then B can take A's eigenvector, the small eigenvector, and just change the eigenvector. So this is why this theorem is interesting. 这个 theorem 的意思就是说 ，A 可以偷拿别人的，如果 A 跟 B commute 的话，那 B 可以偷拿 A 的 eigenvector 来当其他 eigenvector，然后只是 eigenvector 不一样，就是一个神奇的事情。Okay, so theorem just say that theorem is here. Suppose A, B are which are greater than theorem only if there is a total basis. So in this case, then we say we are small, then it's idealized. So this significance is basically that if you want to test whether these two matrices are simultaneously diagonalizable, then you just need to compute its combination. So for example, I want to ask a very trivial question. I want to ask where x and y polynomial has the same eigenvector that can be simultaneously diagonalizable. I don't know how to test it, right? But I can do a computation. Once I do a computation and find it's not zero, I know it's possible. 这个定理的意思就是说，如果我要问一个问题是说，我能不能你给我两个矩阵，我能不能他们会同时被对角化，同时被同样一组 eigenvector 对角化的？或者同一组 basis 对角化的话，我并不知道他们可不可以。因为我不可能同时设置所有的 basis， 但是我可以算这个 computation， 如果 computation 不是零就不行，是零就可以了。So this is non-trivial. So the non-trivial proof is the other direction. So let me say this. So if A and B are simultaneously diagonalized, that means that there exists a basis such that A is a diagonal matrix in that basis, and B is also a diagonal matrix in that basis. So in the same basis, obviously that if there are all diagonal, then A commutes. 你两个对角矩阵相乘，你两个对角矩阵的 commutator 在这里。两个对角矩阵相乘，啊，不就每一个对角线都自己相乘就好，啊，不是一定。所以non-trivial part is that 为什么 commutator 是零的时候，它们同时可以对角？一个方向是 trivial。So the converse is non-trivial. However, I'm asking a converse. Converse means that how to prove that when A is zero, then there are simultaneous diagonalized. Okay, we have 10 minutes, but I can use 10 minutes to give you the proof. So maybe. So this proof is seldom presented in the quantum mechanics or quantum physics. People just tell you this correct. So yeah, we can just I can give you a sketch of proof. So to prove this, we just use the same technique basically in the induction. So we just induction on dimension the matrix dimension. 那这就是一个证明了，就是归纳法。So first one is this. Equals to 1 is good, right? But because when d equals to 1, then A or B are all numbers. So numbers automatically commutes. And they are all down. So let's say for general t for general 2. Let's say I pick eigenbasis, sorry, the eigenspace 1到。所以就是说我把1到来的all the eigens vector span with eigenvector 到达的空间叫出来，叫做1到。Okay, so obviously that one can check that A is back E down to E down. This is trivial because when A times the eigenvector itself become it's just times lambda, right? So it's still in the same space. Now, trivial part is that A will map all the so-called proportional space, the orthogonal space to the that orthogonal space. So let me just write it down. 然后讲一下这个证明。这个证明是说，我们把这个空间叫做1浪达写下来。1浪达是一个 eigenvector 的空间。Right? So let me just record. Right? So 1浪达 going to be the vector v, which is a equals lambda. Okay. And 1浪达 also orthogonal space. Basically also to 1浪达 basically is all the vector. Such that omega x equals to 0 for all x. 这个1到哪就是 eigenstate 生成的空间。1到哪垂直的就是所有的 state， 所有的向量时的所有的这是一个集合，里面每一个元素都是，当你 take x 在1到哪的时候，它跟它内积是0。就是垂直于1到哪的空间，垂直1到哪里面所有的向量都要跟1到哪 per 里面的垂直。So all the vector in 1到哪 per, all the vector in 1到哪 per should also go to all the vector in 1到哪。This is the definition. Okay. So obviously that A will map to 1到哪to 1到哪。This is trivial because A times B will be just lambda times B. still inside this vector space. 没有地方，这个废话。Then so the non-trivial part will be A will map E lambda per E lambda. Why this is true? So A so let's say I take W in I take element W inside this. So the map the results will be A times omega this W, right? But if I give you any vector x, any vector v in E lambda, let's say I take any vector v in E lambda, and I compute this v a with this w. But notice that A is Hermitian, so this is by definition this is the same as a complex conjugate or a they acting on V, right? This is definition of a but A is Hermitian, right? So this is the same as A applied on V with W. But A acting on V is proportional to lambda times V. Okay, so this is lambda times V dot. But V is in E lambda, right? But W is in E the orthogonal space with E lambda. So these are 0. V with W. So that means that this vector A times A applied on W is orthogonal to all the vector in E lambda. So A applied on W would live in this orthogonal space. Okay, so the A is just the A will not trivially act. A will so this A will be break into eigenvector with the eigenspace and it's also so-called normal so-called invariant. So this would be so-called invariant subspace. Okay, so now so notice when we have BA plus AB, right? So this will tell you that B actually also if you take any vector in E lambda and B apply on also C in the same space. Okay, the reason is that let's say I take any V in terms in this E lambda, so let's say I compute AB times B. But AB is the same BA, right? So it's the same as BA times B. But A acting on V is lambda, right? So it's lambda B times B. So B lambda BB is an eigenvector of A. So B times B is an eigenvector of A. Right. So that means that B times B will be still in the eigenspace of line. So B will map E lambda to E lambda. And the similar proof that one can check that B will map E lambda per E lambda. The reason is the same. You just take the same proof. We just take all the W inside E lambda per and we'll apply B W. And B will acting on the left. So it's B times B, you got BB in the product with W. But this BB by definition is also in E lambda. So this guy is in E lambda and the W is E lambda per. So this is 0. So it means that B also maps E lambda per to E lambda. Well, maybe you heard about it, you say, oh, these is so complicated. I don't know what it's talking about. But this the next page you will understand. So what previous proof tell you that there are four mappings. One is A from E lambda to E lambda. And A also preserve the orthogonal space. But B also preserve the same orthogonal space. So that means that if I write B original vector space in terms of E lambda and E lambda per, then I define so-called A lambda per to be the matrix A restricted to the rest of this space. So now A already break into two parts. The first part fixes eigenbasis. The other part fixes on orthogonal space. So if I restrict A to this closed space, A can be viewed as a matrix, but a linear operator but apply on the smaller dimension. And in that smaller dimension, that A lambda and B lambda they all compute. So by the induction, A and B are simultaneously analyzed. 这证明听起来不神奇。我用中文讲，就是说，我们这样造出来这个4个 map 之后，4个 map 之后，我发现 A 跟 B 同时，就是 A 呢，在从 A 会在这个空间上是固定的空间，它不会 map 到别的空间去。所以你把这相关空间切成2块的时候 ，A 在这一块是固定，就是它不会送到外面去，B 也不会。所以我如果把 A 跟 B 限制在这2个小空间上面的时候，它们还是 commute。那我就可以使用数学归纳法，因为我刚刚说他们在 commute 的时候，他们同时可以对角嘛，大家就中了。Okay, so this is the proof. Okay, so we take a break 10 minutes. Yeah. If you don't understand proof, you can ask me.